Hi, I'm Matthew Gallant, and this is a video for IE312 taking a look at friction stir welding and its potential application in the automotive industry as compared to conventional welding, which is used now. So, friction stir welding is a solid state joining process, as opposed to conventional joining processes like welding that we're used to, where things are melted with some difference in voltage, and you're adding metal to the materials to join them together. In friction welding, you have this rotating tool head, which has a large downward force on it, which generates a lot of friction. Then the heat from this friction is usually around 80 to 90% of the melt temperature of the metal that's being joined. So it's important to note at no point in this process is metal being liquefied. It's just being heated up and softened to the point where it can be more easily moved around and plastically deformed. And in this process, there's four main parameters that can be changed. First is the rotation speed, or the speed at which the part head moves. Then there's the downforce, which is what's generating that friction. And there's the weld speed, or the speed at which this tool will actually move across the workpiece. And finally is the tilt angle, which can have an effect on the surface finish of the part. So current industry applications, it's mostly used to join aluminum, titanium, and magnesium alloys. These are alloys which are very hard and don't weld very well at all conventionally. The problem is the conventional welding has this large heat affected zone where the recrystallization makes the metals weaker than they need to be. It's used a lot in aerospace industry, so if you look at the bottom right, you'll see part of a plane fuselage. And what was done traditionally, because they need to use these lightweight, hard aluminum panels, was they would rivet them together because it was thought that those types of alloys couldn't be welded. But they're able to friction stir weld them now, which saves a lot of weight for the airplane, which is important. It's also used in the marine industry. If you look in the top right, you'll see an aluminum hull of a ship, which has been joined together with friction stir welding. And then it's also used for the fuel tanks for spaceships. In the top left, you'll see this massive aluminum fuel tank, which is made with friction stir welding. And it's well suited for manufacturing really large pieces. So advantages with friction stir welding, you get very strong welds, which are stronger than you'd be able to achieve with conventional welding processes. And then you also get increased fatigue life. So that's especially important for an application like an airplane fuselage, where if it's being constantly pressurized and depressurized over the course of the airplane's life, that's going to fatigue those joints. So this is really good for that. You also save a lot of weight. In some cases, or you save 40% of the weight that would be used in a conventional weld. That's really good for aerospace, planes, spaceships, things like that, where they need to shave off every pound they can. And then because there's less temperature being generated, again, it's not reaching the melting temperature, it's less than that. There's decreased residual stress, which makes sense because that stress comes from differences in temperature, and as it cools, it develops those. And then finally, and the most important advantage, is this control over grain size. So conventional welding, you have this big problem in the heat affected zone. But if you look in the bottom right, you'll see that the heat affected zone is actually not too bad for friction stir welding. And then in the stir zone, you get a very hard metal because the grains are really small. And if you look just above that, you'll see that's just sort of to show how weight can be saved You're not adding any material here, you're just stirring up the two metals and mixing the parts together. So limitations, the biggest limitation is the welding speed. This is especially a problem potentially for the automotive industry because if you look at the bottom right, that's what's currently being used, and the weld speeds are a lot higher, and they can also weld at angles as you can see in the picture. You can increase the speed of friction stir welding, but the problem is that results in an increase in temperature, which starts to defeat the purpose of the friction stir weld. If you're just going to increase the temperature, which results in more heat affected zone anyways. Another limitation is tool wear. So you have this rotating tool head, which is exposed to a lot of heat and pressure, and that will wear the tool head out and result in it needing to be replaced, which is costly. There's also limited numerical data. So you can run simulations for friction stir welding on Abaqus and probably SolidWorks. The issue is this is a pretty new technology that was developed during the 90s. So in most cases, they have to actually test the strength of the weld anyway and do a physical test. They're not able to depend on simulation data as much as with processes that have been around for much longer, like casting and subtractive manufacturing. And then the final limitation would be the weld depth. So the weld depth can be pretty good, but it's not unlimited. Usually the source I found said 5 to 65 millimeters for one spindle head. And then if you have another one, you can increase that further. But there are some limitations to it. So final analysis, I would rate the manufacturing readiness level at a 9 because it is being used in industries outside of laboratories successfully. The issue is the industries it's being used in, it's always when it's worth that extra cost to save weight. Is friction stir welding a superior joining method in the automotive industry? I would say no for the vast majority of car manufacturers. Maybe for like a McLaren or Ferrari type, but other than that, it's just not worth it to shave off a few pounds. The problem again is that manufacturing or the welding speed, the current way cars are produced, they weld them very quickly. So for them to be friction stir welded, you would need way more machines to achieve the same rate, which would just not be worth it in terms of cost. Here are the references I used.